It is my true pleasure to welcome Abhinav Kandala from IBM to our session. Abhinav is an experimental physicist at the IBM TJ Watson Research Center and currently leads the Quantum Capabilities and Demonstration team, where he focuses on building tools for executing large quantum circuits and where he explores beyond classical quantum computation. He obtained his bachelor from IIT Bombay and then his PhD in physics from Pennsylvania State University in 2015. Abhinav's current research spans the control and coherence of superconducting qubits, multi-qubit characterization, and near-term applications of quantum computers. And you might all know him as the corresponding author on the paper on evidence for the utility of quantum computing before fault tolerance, which is what we will discuss today. And this was featured on the cover of Nature, received coverage in the New York Times, and he was recognized by MIT Tech Review as one of 35 innovators under 35 for his experiments on error mitigation and molecular simulation with near-term quantum computers. Abhinav, we are extremely excited for your talk today. Please take it away with evidence for the utility of quantum computing before fault tolerance.
Thank you so much for the very kind introduction and the invitation. And I'm particularly excited to hear that many of the students following this program are going to try and replicate parts of our experiment. So I'm actually very curious to see what comes of those efforts. I hope this talk helps some of those efforts and clarifies things or makes it more accessible. And yeah, I'm here for the next hour. So please, go all in with your questions, and I'll try and answer them to the best of my ability. Cool. So before I get started, I really must acknowledge, people who did the work. Youngster Kim and Andrew Edens really did a lot of the heavy lifting for my group on the IBM side. This is, what I'll be talking about is really the journey of methods that we refer to as error mitigation, which are basically geared towards trying to ask the question, is it possible to extract useful information from near-term quantum devices, from noisy quantum devices, before one has fault tolerance? And this is really a path that we've been on for the last maybe 7 years. And I've had the great pleasure of collaborating with Kristen Teme, Sergey Bravi, and Jay Gambetta, primarily driving these questions on the IBM side. For this work specifically, really enjoyed this collaboration. We struck up with Mike Zalotel's group at the University of California, Berkeley. Sajant Anand was the very talented graduate student who ran all the classical simulations, trying to benchmark our circuits, trying to benchmark our circuit executions on our device. But as will be very clear as I walk through the talk, this experiment simply would not have been possible without the contributions of the broader IBM team. It really takes a big team effort to build the kind of devices we're able to, and deploy them and calibrate them and so on. So really, thanks to this entire crowd. Okay, so I'm going to talk through some cliched quotes, perhaps, but I think it's useful to set it up that way. So if one goes back to 1929 even, right? What Dirac said was that the underlying physical laws necessary for the mathematical theory of a large part of physics are completely known. And so, this is something that we now understand. We have the Schrodinger equation that we can use and very successfully to describe many phenomena that we observe in the quantum world. Typically for molecular Hamiltonians, we're looking at for molecular systems, we're looking at Hamiltonians like this. Here is an example of something that describes an interacting spin system. And often we can express these kinds of equations where we want to access, say, static properties like the ground state or the excitation energies, and the task comes down to solving for the eigenvalues and the eigenstates of the Hamiltonian of interest. One can also um, ask, well, how do states evolve in time under under a particular Hamiltonian? So one could be interested in dynamics instead. And these are typically the flavors of questions one can ask. So we know, the point is that we know how to write these equations down, right? But then there's a second part of the code. The difficulty is that the exact applications of these laws leads to equations that are much too complicated to be soluble, right? So we know how to write these equations down, but at a particular scale, trying to solve these equations exactly is extremely difficult, right? And this can be understood by just looking at what these exact solutions require. They basically require some brute force exact diagonalization of of the matrix representation, say, of these Hamiltonians or these states. And as you can see here, this is going to be an exponentially large matrix. For instance, for the Hamiltonian, and trying to store all these matrix elements and manipulate them gets incredibly hard, even at the order of about 50 to 60 qubits. This can require more memory than one has on one of the world's most powerful supercomputers. So this gets very hard very quickly. The only reason we've been able to make tremendous progress in our understanding of several quantum mechanical systems is by relying on classical approximations. Okay? One doesn't have access to exact diagonalization beyond a point, and one has to rely on certain classical approximate methods. Okay, and tensor networks are a very popular way of trying to approximate the many body wave function, for instance, right? And typically one requires some tuning parameter. This is called the bond dimension, which basically controls the level of correlations in your approximation to the quantum state. And to give you some intuition for what this could be like, you basically interpolate between these two extremes. One where you're looking at product states with just a bond dimension of 1. So the state is completely uncorrelated, and then you can have an exact representation of the state, which is going to be very expensive. This is going to have exponential bond dimension. But then you can interpolate between these two, depending on the classical compute resources that you have or the runtime constraints that you have, and also to some extent the properties of the state. So these are one example of classical approximation methods, and I just want to give you a sense for what this classical simulation playbook is like. So what does one do when one develops a new classical simulation method, right? How does one know, in the absence of an exact result, in the absence of an exact solution, how does one know that their classical method is working well, or is it completely wrong? So what are the kind of things you can do? Well, you can have other standard approximate methods, and you can compare to them, and you can ask the question. This is an example of one paper of many thousands that kind of follow this playbook. But you can ask, well, how does this new method that I've developed compare to these other standard methods? The other thing one could do is, well, you could condense the size of the problem. You can reduce it to a smaller size where you can do exact diagonalization. You might have an exact solution. You can also find interesting points where you might be beyond the scale of exact diagonalization, but because of certain symmetries or certain properties, you have access to analytical solutions, so you can benchmark against those, right? That's one thing one can do. Now, I also spoke of aspects like the bond dimension, which can very systematically control the degree of correlation in your wave function approximation, for instance, right? So you can also ask, well, as I systematically increase the correlations, as I systematically increase the amount of classical resources that I want to use to better approximate the state, is it possible to see some convergence right? Is it possible to see that, oh, as I'm increasing the bond dimension, I'm systematically converging to what I believe could be the right answer? And this is also another question that people might ask, right? But the point is here that, yes, you might have convergence, but it's entirely possible that you actually converge to the wrong answer, right? And these are the kind of challenges one has when one operates at the scale beyond exact diagonalization. Okay, so this is a quantum computing talk, and I'm starting the talk talking about classical simulation methods and how these operate, right? And why will hopefully become apparent to you towards the end of the talk. Okay, so these are certain limitations. Approximate classical methods have had a lot of success, but they're very well-known examples where things fail. And of course, this was in Feynman's very famous cliched quote now as well. The spirit of which, of which is that, well, if you want to simulate a quantum system, perhaps you want to have a very well-controlled, programmable quantum device, a quantum computer, basically, right? So here is, one example. Maybe you want to simulate properties of a molecule like one has on the left, of a natural quantum system, and then you could build an artificial quantum system with artificial atoms, such as this quantum processor with 7 superconducting qubits, and one could perhaps control this and manipulate this to learn properties of the natural quantum system that one has on the left. So this was the basic idea, right? And since then there's been a fair bit of progress on many different flavors of quantum computers. At IBM, we focus on superconducting circuits, on superconducting quantum processors, and that's what I'll be talking about. Um, and the primary building block here is a Josephson junction, which is basically a tri-layer stack of an insulator sandwiched between two superconductors. So one has a layer of aluminum oxide that is, for instance, that is sandwiched between two superconductors. One might, very often use something like aluminum, but there've been Josephson junctions made of, a number of different material stacks. And the very nice thing is, one can take this Josephson junction and then and this could be the integral piece in a more complex circuit design. And the interesting aspect is that by tuning these different circuit parameters, one has the ability to engineer the energy levels of the artificial atom that this circuit will now represent, right? So typically, for qubits that you might have heard or referred to as transmon qubits, these Josephson junctions are capacitively shunted, and you can get, very often for the kind of devices we work with, you can get an anharmonic oscillator with unequally spaced energy levels. So you have the bottom two energy levels that you can use as your computational 0 and 1 state, which have a unique frequency, typically about 5 gigahertz. And if you look at the closest transition to that, that would be the 1-2 transition, which is about 300 megahertz away from the primary transition of interest. So these two bottom levels can really be used as the computational 0 and 1 states. And the nice aspect of this, as I said, was you can control these parameters by circuit design. So you have the ability to really engineer these artificial atoms, and the transmons are just one example of this, but there have been many other flavors as well. But these have largely been the most popular ones towards building the large processors. Okay, so this is all very nice. We can do all the different ingredients that one needs to do quantum computation with these devices. We can basically tick off many aspects of the De Vincenzo criteria. One can drive single qubit operations, 2 qubit operations. One can read out these qubits individually. I won't go into those details in this talk. I assume over the course of the program there have been introductions to these aspects as well. But if there are any questions, I'm happy to answer them towards at any point. But the one challenge I do want to talk about as well, the aspect of noise, which is that we can make these beautiful qubits, but then there's just noise that's inherent to these systems, right? And one very classic example is that of energy relaxation. For instance, if you try and prepare the qubit in its excited state in the computational one state and just let it relax, there will be a certain time scale over which it will it will decay back to its ground state, to the zero state, right? So you're basically losing this quantum information over these time scales. So if you try and get some sense of what that time scale is, this is typically referred to as the T1 time. Okay, so this is one classic example of incoherent errors from energy relaxation. But there are many other kinds of errors. You can have dephasing. I showed you what these transmon energy levels look like. You can have leakage out of the computational subspace. You can have crosstalk errors. You can have control errors where you intend to perform a rotation of a particular angle, but actually what happens in practice is a different angle. So there are all kinds of errors that one is constantly dealing with on all the qubits across the processor, right? So if you actually want to implement and program this device and send to it a series of operations, right? You want to run a quantum program with single qubit operations shown in the red blocks and the blue blocks representing two qubit entangling operations. You want to send a sequence of these and measure the output. What's actually happening over time is that the circuit implementation is getting increasingly noisy, and that's what I'm trying to represent by all of these jagged edges and the fading, that you're just accumulating noise as you're trying to run your quantum circuit. Okay, and this is the problem, and this has been very well known, right? And basically, if you want to think about why has it been so challenging, some of these quotes from Feynman are from the 80s, and we're 45, 50 years later. Why are we still struggling to build these all-powerful quantum computers? And if you try and compare this to the kind of error rates one has or the noise one has on classical devices, we're talking of a difference of over 20 orders of magnitude. Okay, so that really makes it incredibly challenging, or much more challenging to build these quantum computers. And what's really you know uh, the obvious path forward is there has to be some way in which one can fix these errors. And when errors happen on classical devices, there are mechanisms with which one can correct for these errors, and it's just a little easier because the inherent error rates are much smaller. Okay, and so this also is not something new. These ideas have been known for decades, and in the 90s one had the first ideas of quantum error correction, and the idea basically here is that you want to delocalize your quantum information over a much larger network of qubits. And so when you have local errors, the state doesn't get corrupted as much as quickly, and these errors happen sufficiently slowly that you can detect them and then correct for them. And that's basically been this very well-known theoretical formalism, which one doesn't quite have a large-scale implementation of this yet, because this is a very, very challenging task, and there are many challenging pieces to this. Okay, but along these lines, at IBM, we've been building increasingly complex networks of qubits. We build these devices in this heavy hex architecture, and we've gone up to even 1,000 qubits, trying to solve many hardware scaling challenges along the way, and really have these technologies developed. But then basically, even as you go beyond the 65 qubit scale, right? With these hummingbird devices, these are already basically a scale where the devices are noisy, yes, but there is a scale that's beyond the scale of brute force classical computation, beyond the scale of exact diagonalization. Okay, so we have these large devices now. which are at a scale beyond exact classical simulation or brute force classical simulation. But we don't have full fault tolerance. And the key question here then is, what can we do with these systems in the absence of fault tolerance? And this is really, a question that I myself am deeply motivated by. Right. So let's let's try and do a quick estimation to get a sense of what this would look like in the absence of fault tolerance. Say I had a simple quantum circuit, 100 qubits, perhaps 10,000 2-qubit gates. Okay, so that's the circuit. And you can ask, well, how accurate is every gate in the presence of noise? And these could be accurate to a degree of 99.9%. And the technical phrase here is fidelity. Okay. But these are possible. Like these are numbers one can achieve on superconducting qubits today. It's kind of the state of the art, but this is possible. So then if you ask, well, if I ran 10,000 of these gates, what would be the fidelity of the state that I prepare? And that is going to be a very, very lousy fidelity, 5e minus 4. And basically what this means is if I'm asking the question, the final state I prepare, what's the overlap of that with the ideal state that would have been prepared in the absence of noise? Okay. So if these states are this lousy, is there anything useful one can do with these devices? Is there any useful computation, any useful information I can extract? Okay, and then one can ask the question, well, maybe the task of preserving the quantum state is actually quite challenging, and this is what quantum error correction attempts to do. But even though the fidelity is very bad or very poor, perhaps it might be possible to estimate certain properties of the ideal state, even though I'm preparing the noisy state. Okay? And to give you some intuition for this, this is an example I find very useful. It's very, very simple and perhaps too simple, but it's a useful picture to have, right? So if I imagine I had a chain of 1,000 spins all aligned in the same direction, and I flip just one of these, and I ask the question, what's the overlap of these two? The fidelity is going to be 0, right? But instead, if I ask the question, well, what is the global magnetization of the system, right? This singular flip is only going to change the estimate in the third digit, right? So one could actually have a pretty good estimate of what that magnetization is, even though the fidelity is completely atrocious. Fidelity can be viewed as, a worst case metric. And the intuition I want to give you is there might be certain properties of that ideal state which we can get a reasonable approximation for, even with these very low fidelities. Okay, so then the question is, well, measuring these kinds of properties like the magnetization of a spin system, are these interesting? Are these kinds of observables, expectation values, interesting in the context of quantum algorithms, right? And actually, it turns out there is. Okay, there's a lot of interest there. So in these noisy near-term devices, we have noise, and that's going to limit the number of operations we can run, right? So the kind of circuits one can run and hope to get some useful information, these are typically going to be what are called short depth quantum circuits. And what that basically means is the number of entangling layers in the circuit will be a smallish number. Okay. In this case, this entire block, if you can see my cursor, is a depth of 1, this is depth 2, and basically this entire circuit is a depth 5 circuit. And then you want to run a short depth quantum circuit like this, and then measure properties like that magnetization of that spin chain, right? You want to measure certain observables. And this really is the core primitive of the vast majority of near-term quantum algorithms. The measurement of expectation values after running a short depth quantum circuit. Okay. And basically, if you look at things like variational quantum eigensolvers, where you're interested in measuring the binding energies of small molecules, cost functions and optimization problems, correlation functions for quantum antibody systems, the example of magnetization that you just saw. All of these are examples of, where if you tried mapping these problems on a quantum processor, it really gets down to trying to map this onto a short-depth quantum circuit and the measurement of certain expectation values. So this was something we began to explore, even in 2017, where we wanted to see, well, what can these existing devices do? This was a device with about 7 qubits, right? And then one of the calculations we tried to run here was trying to estimate the binding energies of lithium hydride, a problem that we mapped onto just 4 qubits. And the error rates were pretty large back then. There was a lot of noise, basically, and we couldn't run too deep a circuit. So these were just circuits with a depth of 2. So there's 2 entangling blocks. Because this is a 4-qubit problem, you already know what the answer is supposed to be. You can do this. You can do the exact diagonalization very, very trivially. And so you know what the energy curve is. And if you look at the results from the quantum device, these were pretty horrendous, right? Particularly in the context of quantum chemistry, one is often looking for accuracies that are at least like 2 orders of magnitude better than the kind of numbers we were getting here. And so already on these very simplistic problems that actually no chemist would care about, one is seeing very poor poor results from the quantum device. This is noisy. And so then the question is then, well, is it really possible at all then that a noisy quantum computer can produce accurate expectation values before fault tolerance? Okay. In that experiment, it didn't seem to be the case. And then 2, which is crucial, particularly in the context of being at a scale where one only has classical approximations, can this be achieved at this scale beyond brute force, beyond the scale of exact diagonalization? Okay, so there are these 2 very important questions, and I will try and show you in this talk that the answer to both is yes. Okay, so the first question was really addressed by this paper, essentially inventing error mitigation techniques, and there was simultaneous work from the Oxford group of Simon Benjamin, and I'll largely focus on one of the methods in this paper. It's called zero noise extrapolation. But the basic idea of these methods is that, well, if one has the ability to characterize the noise, then we can use our knowledge of that noise to manipulate its effect. And then by doing this manipulation, you can effectively undo the effect of the noise in your computation. Okay, so these are the basic steps in these error mitigation protocols. And this is not, like you might be more familiar with things like noise canceling headphones, for instance, right? Which have, to some sense, some parts of these operating principles, right? You have knowledge of what the background noise is, and then you do things to null its effect. And that's basically what the spirit of these methods is. And the nice aspect here is that one wants to do this without having the overhead of trying to build this large network of qubits and delocalize your information. So you want to do this without the overhead of an increased qubit count. Okay. So this method, as I said, I was going to talk about zero noise extrapolation. The basic idea here is that you have some expectation value like that energy, that binding energy, and you can express this as a Taylor series in some noise factor, lambda, and the basic idea is one wants to access this zero noise limit. Okay, so what is this expectation value in the absence of noise? That basically amounts to trying to suppress all of these additional higher order noise terms. So if I, as an experimentalist, had the ability to really amplify the noise very precisely, okay, And so let me say that I did my initial measurement and I got a noisy a noisy expectation value. I'm including all the higher order noise terms in this everything that's beyond linear. And now say I had the ability somehow to really tune the T1 and T2 of the device, for instance, and then amplify the noise precisely by a factor of C. I can rerun these experiments, right? And I now get a new estimate. And now by combining these two, you can basically see that you suppress this term, this leading order term. Okay? And essentially, this can be extended. This is linear extrapolation. One can, in principle, have n such noisy measurements, and you can suppress basically the leading order noise term to order lambda to the n. And this is basically Richardson extrapolation. It's a very, very popular tool in classical methods as well, right? At some point you will be limited by sampling noise, but the question is, well, how does one actually amplify this noise in this precise manner, right? For that, you need to even know the noise. You need to characterize the noise. Okay, and this bit over the next 4 or 5 slides is going to be a little technical. So once again, please feel free to interrupt me. I'll just give you some flavor for what these protocols look like. And I'm going to talk about a simple 1-qubit example. Okay, so what this block represents here is the noisy unitary. Okay, so you have say a noisy gate, and then you want to, of course, measure an expectation value, and that's what you're going to measure here. You're going to measure the noisy expectation value, A tilde, and basically this can be modeled as an ideal unitary with some noise channel. Okay, and now if I want to amplify the noise by a factor of 2, this can be modeled as slapping on an additional noise channel. Okay, and now just for the purpose of this discussion, let's just assume that this noise is very simple, and it's a very simple poly channel with some bit flip probability p, and this is something I have characterized, and I know what p is here. And basically, if I take this and I insert it in here by linearity, what I can basically see is that the task of accessing this expectation value at this amplified noise strength at a factor of 2 basically amounts to sampling between these two circuits. Okay, so I'm going to sample circuits where I now introduce an identity gate with probability 1 minus p, and a probability and an X gate before my noisy unitary of interest with a probability p. Okay, so what this implementation is going to look like is something like this. Okay, and if I'm going to average over these results, I am going to access this expectation value at this amplified noise rate of 2, right? But this required me to know what P is. And I need to characterize what that P is, right? And okay, I basically took this very simple example with just bit flip errors, but in principle, I could have a more complex noise channel, poly channel, for instance, here, and that would basically amount to sampling those terms as well in this. And I also just walked through a very simple example of trying to amplify the noise by a factor of 2, but that as well can in principle be done at arbitrary noise factors, right? You can do this at like 1.5, 3, whatever. If you go very large, you'll end up having too much noise in your circuit. But also, interestingly, you can also go in the opposite direction, and there's also what's called probabilistic error cancellation, where at exponential sampling overhead, you can actually completely suppress the noise. And I won't go into these details for now, but I just want to give you a sense that this G can be taken back down to 0 as well. Okay. Now, I walked through this very simple example of just 1 qubit, but what we actually have are these circuits with a large number of qubits and lots of operations, right? And now the task of trying to characterize the noise on a large quantum circuit That's very challenging. Okay. That's once again trying to describe that noise channel is an exponentially challenging problem. You just have a like 4 to the n by 4 to the n parameters. And then the question once again becomes, well, how can we learn the noise? We need to characterize the noise to know how to manipulate it, right? To know how to amplify the noise. And once we're able to do that, then we can basically effectively null its effect by doing tricks like zero noise extrapolation, right? So I'm going to be skipping some details here, but I encourage you to check out this paper if you're interested. But basically, to make the task of noise characterization more practical, you have to make some assumptions. You have to make some assumptions on the locality of the noise. And here, you can make the assumption that, well, the generators of the noise basically are local, and they're basically confined to connected qubits on the device. So there isn't like a strong correlation between the generators of the noise on, say, this qubit here and that qubit here. And these can be reasonable approximations. And one can ask if this is truly a valid approximation or not, and so on. But one needs to make certain approximations. And once that's done, you can basically reduce this complexity from having 10 to the 76 parameters or 10 to the 77 parameters. Maybe you should check my math on that as well. But that can be reduced to about 1,000 to 2,000 parameters, really, and that's much more manageable, to really characterize the noise on a 127 qubit device. And how those parameters are learned, once again, there's a lot of literature on this. I'll encourage you to read this paper. But basically, each of these colors here represent the values of one of those noise parameters. We're basically looking at, for every qubit, for every individual qubit, there are 3 parameters that are used to model the noise, and then for every connected pair, one has 9 parameters. Yeah. Okay. So basically, what this looks like is, once you have access to this noise channel, once you have access to this noise model, we're going to controllably amplify the noise by running several circuits where we insert, gates like this, depending on the noise terms that we have in the noise channel, right? So based on our knowledge of the noise. And this is very similar to the 1 qubit example, just an extension of this to a larger circuit. And to give you some sense of what this looks like in practice, this is an example of a 127 qubit experiment from the paper, and this is some circuit was run for now. For the time being, let's not focus on that. And then there's some observable which needs to take the value of 1. When you run it at the bare noise limit, at the bare noise value, this is G equals to 1. It's very biased from the ideal result. You have this big error here. But now you can run the same circuit at different noise levels based on the knowledge of the noise. So here we run it at a factor of 1.2 and 1.6, and now the error is even more in the observable. But we can use these 3 noisy estimates to extrapolate back to what the result could have been in the absence of noise. Okay. So with linear extrapolation, you suppress, all your quadratic and higher order noise terms, but that leaves behind some bias. But then, another paper from Simon Benjamin's group was on exponential extrapolation, which we actually saw worked, a lot better, and that was what we used largely in this work. Okay, so this is the machinery that we're going to try and use to extract useful information, even from these very noisy devices where we prepare states with incredibly low fidelity. Okay, so before I go to how we used all of this machinery, I'll pause again for any questions.
Yes, wonderful. I see a couple of people typing. Earlier, there was a question by Eros. Is the problem simply noise? It looks like additive white Gaussian noise, which should be relatively easy to filter. Why was this not the case here?
It's not necessarily just that. Noise can be very, very complicated. One can have one can have noise from, as I said, energy relaxation and dephasing, but there can also be other kinds of uh, of coherent errors, which can come from the electronics, for instance, or poor calibrations, where you intended to perform a 90-degree rotation, but it actually turns out to be 91 degrees, and this can happen on different gates to different degrees. Um, um, the coherence times, also might not be uniform across the entire device. Some devices, some qubits might have better coherence times than others. So it's actually it's not as easy to model the noise in the entire circuit.
Great, thank you very much.
So we had all this machinery, and now we want to ask, what should we apply this to? And one one very popular problem in many aspects of physics is studying the time dynamics of a transverse field Ising model. Okay, so here let me just try and yeah. So here one has a Hamiltonian of this kind. You have the ZZ interaction between connected pairs, and then one has a transverse field, and you basically have these two parameters that quantify the strength of these two interactions. And basically, one asks the question: well, if I turn on this interaction at time t equal to 0, how does the system evolve? And what is the system? I'm going to define the system to be a spin lattice that shares the hardware topology of the quantum processor. So a 127 qubit spin lattice that shares, the topology of the device. And then the kind of questions one might ask, well, is like, how does the magnetization evolve in time? I start in some initial state, some initial magnetization, and now I start some evolution. How does the system evolve? Or if I fix the evolution time and I sweep one of these parameters, like such as the transverse field, for instance, how does the magnetization evolve as one does that, right? And basically trying to ask these questions gets down to trying to map this onto a quantum circuit. Okay, and basically one can look at this as a trotterized circuit where you discretize this time evolution, and then you're going to have blocks that you keep repeating. And then in each block, you're going to have single qubit rotations that basically are going to be related to this H parameter. So you can tune the transverse field by the single qubit gates. And then you want to drive ZZ interactions and all these connected qubits, which are basically now the spins. The way you can drive these interactions are by entangling two qubit gates by these ZZ gates. The way these can be implemented are basically you can drive gates that are not nearest neighbors in parallel, right? So what that means for this kind of connectivity is you can apply all these green interactions in parallel. That's going to be one block. You can apply all the blue interactions in parallel. That's going to be another block. You can implement the red in another block. And basically each of these blocks is now going to be a different layer. One can do the noise characterization on each of these layers and then controllably amplify the noise in each of these layers. Okay. Okay. Now, the first experiment we ran was 127 qubits at 15 entangling layers. And now at 127 qubits, you're already at a scale beyond what one can do with exact diagonalization. The first thing you want to do is you want to build trust in your quantum processor. You want to know that these methods and this device is capable of doing something accurately. And so there are two very interesting points, and these are called Clifford points, because the circuit that you run, if you fix these ZZ angles to pi over 2, and the single qubit rotations to 0 or pi over 2, then that circuit is Clifford. And because of certain properties of this family of circuits at these parameter values, you actually have solutions that you can estimate efficiently. So here we knew the answer was supposed to be 1. Here, the answer was supposed to be 0. In the presence of noise, you get some bias from the correct answer. But then I'm not showing the values of the amplified noise rates, but in principle, you can amplify that noise and extrapolate to something that's much closer to 1 here and something it's fairly close to 0. So at both these cases, we built a fair amount of trust that the methods were working quite well. The device is working quite well. Now what we begin to do is we begin to sweep this theta angle between 0 and pi over 2. And we try and see how this evolution is. Once again, in the absence of noise, that's in the presence of noise for the base noise level, in the absence of mitigation, basically you see this evolution here. That's the green trace. And then once you do the error mitigation, you see this bump up. And then that's the evolution you have. Now, at these intermediate points, one can't do exact diagonalization. And the question was, well, what do we compare to here, right? So now if you remember the classical simulation playbook, what does one do when one has classical methods that are beyond, that we want to verify the performance, or we want to benchmark the performance at a scale where one doesn't have access to an exact solution? We compare to existing standard methods, right? And so, for this, we really approached Mike Zalatal's group at Berkeley and tried to ask, well, can we compare this to other classical methods? And these were two methods that we compared to. This was one of these, is basically called matrix product states. It's very similar to, it's actually identical to the example I showed when I introduced tensor network methods. ISO-TNS is a 2D generalization of this. And basically, what we saw was that at these initial theta angles, there was very good agreement. And then essentially, as you increase your theta, you increase the degree of entanglement in the circuit. And then we began to see these deviations from the quantum computation. And our immediate reaction, of course, was that, oh, well, the device has gotten too noisy. So clearly, as we make the circuits a little more challenging, the experiment begins to decay much faster. Okay. What we then realized, and this is, if I didn't emphasize this already, this is basically asking, asking the question of the global magnetization of all 127 qubits. So then what we realized was that this you can actually access by measuring the single site magnetizations, okay? And because the circuit depth is only 15 layers, it's not very deep. If you try and trace back what is referred to as the light cone, so you basically trace back from the observable of interest, here this would be just a single site observable. You ask the question, which gates in this entire circuit actually affect the accuracy of this observable, okay? And then you're going to have this kind of light cone. So even though the qubit number across the entire circuit that was run was all 127 qubits, you can have a much smaller number of qubits in this light cone. And if you have that, then with that smaller number of qubits, you might be able to do exact diagonalization. And it actually turns out that this was indeed the case for circuits of this volume. So because of this trick that's specific to this reduced depth and the particular observable that we had, we were able to access this exact trace using this light cone trick. And then what we actually see is that the experimental points are actually really good. They have tremendous agreement with this exact simulation. So this was really exciting to see. Okay, and then the obvious thing is you want to increase the complexity of the experiment. We looked at even more complex observables. But then I want to just fast forward to the point now beyond exact verification, where you make the circuit sufficiently deep that you can't access these light cone tricks anymore, and you don't have access to this. And basically, the spirit of what I'm going to tell you again is referring back to the classical simulation playbook, right? We tried to push this experiment to beyond exactly verifiable regimes, and then there were a number of classical methods that were also attempted, both by our collaboration with Berkeley and several other groups. And if you try and plot the computations from the results from all of these different computations, okay, that's what this plot looks like. Okay, and they're all in the same color, and I haven't told you which of these comes from which method. Okay, and now if I now highlight one of these colors, one of these is now from a quantum computer, from an error-mitigated quantum computation. Okay, so that's now the space we're getting into. We have this about 20% uncertainty between all of these methods, all of these different benchmarking attempts at this very, a fairly simple circuit. And then one of these points or one of these traces comes from this error-mitigated quantum device, right? And now if I color code all of these, then you can see that all of uh, uh, these different methods correspond to classical simulation attempts from different groups, right? So this is once again an extension of that playbook, right? What does one do when one has a new classical simulation method? Essentially, what we now have is a new computational tool where quantum computers today are capable, despite of noise, are capable of producing results with a fair amount of accuracy, where you can compare with other classical methods and see that within the uncertainty of these different approximations, you can have results from a quantum device. And you're now able to do this at a scale which is beyond where one has access to an exact solution from brute force diagonalization. Okay, so that's the spirit of what we're trying to say. This we're seeing as evidence for the utility of quantum computing before fault tolerance, right? And then I think I'm already over time, so maybe I shouldn't spend too much time on this. But I just want to give you a flavor of what's happened since the paper. There've been many more examples of 100-qubit experiments, both run from IBM, but also by other users of our devices. And this is only going to increase. You're only going to see more of these utility scale computations being run on these, which will increasingly give more trust in the methods, in the error mitigation methods, and what one can do in the device. And really, the crux here is we have devices where we can characterize the noise fairly well, we can manipulate it and null its effect. Okay. That said, we're also improving the devices tremendously. We have devices with much better error rates than what we had in this paper. That's going to you're going to see lots of examples now coming through with even more challenging computations that are run on these devices. I spoke of noise characterization. For the experts who've used superconducting qubits, in the past, you'll see that things like T1 times can fluctuate all over the place, and really on unpredictable timescales, and that has some challenge to your noise characterization. When you characterize the noise might be something, but when you try and amplify it or cancel it and mitigate its effect, it might be something else, and that can really lead to incorrect error mitigation. But in this most recent paper that we had out this month, we've shown examples with we've shown a path to stabilizing the noise on these, and that's going to be a really powerful technique. We've also had even more advances in error mitigation, extending these kinds of methods to circuits with mid-circuit measurements and feed forward operations. And I think a very, very attractive near-term path is going to be of quantum and classical. And you might have seen this very nice paper leveraging a quantum computer in sync with HPC to really extend the kind of molecular simulations one can do, to even about 77 qubits. But in other ways, where this is going to be very, very attractive is in trying to increase the kind of circuit depths that we can simulate with these noisy devices. You can have a very large circuit depth, which if you try to run completely on your quantum device, it's going to be way too noisy in the absence of error correction. But then you can basically imagine methods where a part of the circuit you simulate on the quantum device, the other part you simulate on HPC, and effectively now by combining this, you're able to simulate larger quantum circuits than what was previously possible. So I think this is going to be a very crucial direction where one can hope to go from, the kind of computations I showed, demonstrating utility, demonstrating accuracy, to actually some kind of quantum advantage. But so in the last year, there's a lot that's happened. There's going to be an increasing back and forth, I think, between quantum methods, between classical simulation methods and these quantum experiments. And all of this will tell us where those interesting, challenging circuits lie. To give you some more optimism for where the hardware is going, really they're like order of magnitudes improvement in both error rates and coherence times that we're looking at, that we're hoping to tap into our next generation devices, which will really enable much more challenging, complex computations to be run on these with error mitigation. I think my slides have decided to hang. But yeah, I'll leave these take-home messages up there and try and take any final questions.
Fantastic. Thank you very much for this great talk, Abhinav. Really exciting, and also very exciting how it's going hand in hand with the developments in hardware. Pradhan, I see new questions popping up. Could you please share them?
Yes, so the questions haven't stopped since the last time we took a break. The participants are really excited on the score. Amazing session once again, Abhinav. So let me start fielding the questions one by one. Okay, so the first question is, this is a good one. So if we had a problem that could not be run classically, its classical solution is not possible because it might take thousands and millions of years, how do we check if our quantum solution is correct if we do not have anything to compare with?
Oh, that's a terrific question. Yes. So the short answer is maybe you can't. And then what you have to do is you have to rely on other ways to trust that your quantum device is producing the right result. So like, the example I showed here, where you first build trust in the methods that you use, in the devices that you use, by running circuits in regimes where you might know what the analytical solution is. Okay? And that's going to help you build trust in the quantum device. Now, if you want to go beyond the realm of just computations, so say that your actual computation that you were interested in was, oh, I want to know what the binding energy of a molecule is. Then what you could do is, well, you can actually go and do that experiment, right? If you can actually go and try and break the bond in that molecule of interest, and then you measure some energy that reflects that binding energy, and you try and compare to that experimentally measured number. So that's another way in practice how one could verify computations that are beyond where one can access the exact solution.
Great. Thanks, Abhinav. We have another question from Itan Esanfar, and the question is that you earlier mentioned something about amplifying the noise.
Mm-hmm.
Now he thinks that one might intentionally imagine that we would want to diminish or remove the noise.
Mm-hmm.
Why are we amplifying it?
That's a great question. So certainly you can also cancel the noise as well. Oops. Okay. Okay. So yes. So once you have a noise channel, like in this example, you can also try and invert this noise channel, right? And that's what this is going to look like. And the reason you have this kind of gamma term here is I've tried to express this as a quasi-probability distribution. So you still have the reason I call it quasi is because you have some negative signs in here. But I want to still implement these as circuits I can sample this way, right? So that when I collect and I average the results from all of these multiple circuits in the correct way, I get access to that effectively amplified or effectively canceled noise. All right. So this is going to be the kind of prefactor I have. And then once again, it really amounts to running circuits with identity or X. The only difference here is going to be that to keep track of the averaging the correct way, I will have to account for this negative sign. So every time I have an X, I'm going to put a negative sign on the shot that I measure there. But this gamma is going to be a sampling overhead. So this is going to increase the variance of the observable I measure, and this is going to blow up exponentially, because essentially you're going to have a gamma for every gate in the circuit. So the net overhead for the entire device can really be something that goes as gamma to the power of nd. And basically this is what that kind of sampling overhead for the entire device could look like. And this is really the game of error mitigation. You have exponential sampling overhead, but if you bring this gamma down, if you bring this base down, and as you saw in that plot, gamma was a function of p, right? P was the error rate essentially there. Smaller the p, the closer gamma is going to be towards 1. So you can, once again, you can try and do the math for 100 qubits with a depth of 100. What happens if gamma is 1.01 versus what happens if gamma is 1.001, right? And you'll see this dramatic drop in the kind of sampling overhead that one might have. And this can really make things much more feasible. And this is actually a far more powerful method than just the amplification. And this is something, this is one of the additional powerful error mitigation methods I was talking about. The examples I showed were largely just weight 1 observables with the magnetization. We had a few other examples in the paper, but this is really a 50 qubit example of this method in practice where we cancel the noise instead of amplifying it. And you can really, see how you can recover signal that's this much in the noise and try and get it back towards its right value, which was close to 1 on observables, which are basically weight 49. So 49 of those terms are non-identity. And so this is absolutely the most powerful error mitigation method in my opinion.
Thank you very much, Abhinav. And also, while we have so many postdocs here, so many PhD students, many undergrads, would you like to share a message with them while everyone is sculpting their quantum studies and then also quantum careers? What would you like to share with everyone who is working hard to basically get there where you are?
That's an interesting question. I think it's a moving target for everyone. So I don't consider myself too different from any of you. I think there are always things we don't understand. I think after my PhD, I tried. I was basically switching fields to quantum computing. I didn't formally do my PhD in quantum computing. I was more of a condensed matter experimentalist. And certainly, yeah, it's a lot of material. There are so many different things, aspects of hardware, algorithms, error correction, now error mitigation. And it's very easy to get overwhelmed with how much one doesn't know. And one thing I found very helpful was even people I perceived as experts, don't know everything, and it's still possible to be very productive, and I think over the course of your education, basically what you're equipped to do is to try and learn whatever you want to learn, and I think it's useful to get comfortable with what's not understood and actually be driven by it, to try and just do projects that help you solve those questions. And I think that's a never-ending process. It happens if you're a postdoc. I think it happens if you're an undergrad. It also happens if you're a PI. It's just a never-ending journey. So I think,
Amazing.
Yeah.
Thank you so much for sharing that advice. And everyone here is doing exactly that, going in the breadth, but then also going more in depth. So glad you were willing to speak here today, Abhinav. Wonderful lecture. Thank you very much and have a great rest of the day.